just look at it while you're eating. Just think about it. So what their mistake they're making is, you've got 446 people, and you're trying to take. So your sample's 446, and so you're going to ask yourself, what would I expect if everything was even? And so I can play with it while we're talking. If everything was even, and I just got a blank Excel in here, we would think we would have 446 divided by 12. Yeah, we think we would have 37 people born in each month. January, February, March, April. Everything was just completely random and perfect. So they said they got 30% more. So they got what, a third of that's 12. They got somewhere 48, 49. They're like, oh, this is, clearly tells us that we got a problem. Well, so what initially he says in his write-up, he said, well, yeah, if you don't think about it correctly, this is a binomial distribution. So I was going to make us a quick binomial distribution just to play with. This is because if they had done this, they wouldn't have published their results, and it only takes 5 minutes. So let me make a binomial distribution. I guess it came up, right? I should have looked because I don't know what it's that. Okay. I don't know if this is new or old. You can use the old and the new. Right? The binomial distribution, and I want to know what's the chances of getting roughly 48. 48 out of, I don't know, what was it, 446? 446, and our probability is what? 1 in 12, right? We've got one month out of the year, and we do not want a cumulative distribution, so we're going to say false. Okay, so there's that. So there's our scientific experiment. I'm going to drag down here just. And so I'm going to ask, what was the possibility of getting a 10? What's the possibility of getting 20, 30? Okay, so now let me. I'm sorry. What did I do wrong? I know what I did wrong. Yeah, I was stupid. I don't want. What's the possibility of getting 48? So what's the possibility of getting 10? The whole point of this little thing. And then the next one, what's the possibility of getting 20? So just dragging on down and kind of do a bunch of them. Much better with my report. Let's see. Just give you time to eat and move the phone around with it. There we go. Okay, so here we go. Okay, so now. There, so kind of, instead of using 48, we'll use 50 or so. Let's see. So, or 30. Yeah, see, here we are. So, yeah, so the probability of getting 40 in here is, 5%. Yeah. So even getting 40 out of 37 is 5%. And let's see. I'll do 48 just so we can get, because I think he claims it was like 3%. Yeah, okay, so I get like 2%, so, yeah. So the chances are 1.2% that this would have happened, but what's happening is, you're not just doing it once, right? You're asking it 12 times. You're asking it in because you took all of these and then you took the maximum. So you took how many were born in January, how many were born in February, how many were born in March, how many were born in April. So if you just used a binomial distribution and you said, well, yeah, that's kind of unlikely, but that wasn't what he used. He used the binomial distribution, he sampled it, he used it 12 times because he asked about January, February, March, April, May, and he picked the biggest. So because he picked the biggest, it becomes now not the binomial distribution, because you did it 12 times and pick the biggest, it becomes an extreme value type problem. And he writes the mathematics in there. So really, if you look at it, let's see, if you look at it, I did it over here, just for fun. So what I did, I just had however many trials. I think I did 446 too, but maybe I did 500. And I just had it randomly pick a number between 1 and 12 and say that was the month you were born in, and then went through and counted. Looky here. 43, 39, 40, how many times you were born, how many times you had somebody be born in that month, and then I did it a bunch of times. Let's see how many times did I do it. Yeah, I did it over here. I did it once, and I redo the random numbers, and I did it 30 times. Yeah, I thought I did it 30 times. So what I'm saying is I set up this experiment, had my 446 women, did it 30 times, took the average of the maximum, you know, and the average of the maximum was 46. So I did an experiment that took me maybe 15 minutes to show that if I had a random sample, 446 people, and asked, you know, which month were they born in, and nothing about anorexia, I just randomly assigned them a birth month with equal probability, and then looked and saw what's the maximum number born in the month that had the maximum, and just did that 30 times. I said, well, it was 46. So that you know, so what it says, it's not unusual. It's not weird. It wasn't weird that you had a number of 46 people born in June. In fact, it was just random statistics, random math. And so if they had understood these silly statistics, they wouldn't have made this mistake. They wouldn't have made these measurements and said, oh my gosh, look, June stands out. You know, what it says is, I could go and, you know, take 500 people that work at Y12, run this same experiment, look at the month and say that, oh gee, you know, it seems like on average 48 of them were born in February instead of the average of 37, and so gosh, people work at Y12 must be born in February, and come up with some ridiculous supposition as to why that's so. So I guess some of the lessons learned from this silliness is, you know, be careful with how you apply things. Understand what you're doing, or if it seems weird, you know, what's wrong with doing an experiment like this? I guess, you know, think about. I mean, you know, it only took you 15 minutes to do this. The hardest part was to kind of figure out how to do the getting the 1 to appear in the month, you know, with my if statement. You know, and then once I had 2 or 3 lines, you know, you can always just copy them and pull them down in Excel, and you know. And then, well, I had to sit there and run it 30 times and write the answer down. Yeah, you know, I got 53 once for the maximum. Look, 47, 43. Yeah, so it's just an interesting thing. It's an interesting thing how people constantly make these kind of mistakes. And again, remember I said early on, if you don't have a good science basis for the causality, don't go down that path. You know, try to do the statistics. Try to get the science before the statistics is what I would like to do. Now, I know that's contradictory to a lot of these data mining and type approaches, but if you come up with some conclusion, gosh, at least be able to substantiate it with some science, I guess, or some good causality. So now, let's see. So back to here. So what they're saying on this slide is, instead of using the binomial disk like I did in Excel, there are tables of this stuff, you know, like in the older days when you had the CRC handbook, and you could look it up. So for example, you've got 10 samples. I've got a probability of 35% of having my event of interest occurring. I'm going to ask myself, what's the probability that I'm going to get 3 events of interest? So let's see, 3 events of interest, probability of 35, that's this one, 25%. Yeah, that's amazing. Now I've got 10, same thing, 10 events. I got a 75% chance of my event of interest. What's my probability of getting 8? They say it's really tiny. Now that really bugged me when I first looked at this slide, and I left it on here. I was like, wait a minute, that's exactly the opposite. Think about our little machine one I did early on with the 4. And I put 75% in, and it was way skewed to the right. This is way skewed to the left. This is almost nothing. They goofed up, okay? So I'll put it in Excel. The real answer is there. So you can see what they've done. They've read their table wrong. Right? Because you have to ask yourself, why do the numbers, the X's go down over here, and go up over here, well, you know what it is. It's the ups correspond to here, even though I don't have the directions for the table. You got, you look at this and you say, no, wait a minute, X is going down, X is going up. There's got to be a reason, and you know that these things are symmetrical. The 25% 2 chance, well, yeah, it's the same as the 25% 2, right, is the same as the 875. You can tell that from the table. So they've read this wrong. The real answer is that one. Yeah, 75 and 8. But, I'll read the table when you plug it into Excel. But anyway, I guess what I wanted to point that out, I always question things, right? If something looks strange, it is, or if something's got something going 2 different ways, there's a reason. Think about it, it's kind of interesting too. Or don't use the tables, right? Use Excel. Okay, so what are the characteristics of the binomial distribution? Here's its average, the mean, n times pi. Here's its standard deviation, n times pi times 1 minus pi, where, pi was our probability of end of interest. That's not exactly straightforward, is it? It's not. I mean, to think that, and we saw that, right? Remember with the 4 one, I had 4, total n was 4, and my pi was 50-50, the average is 2. So we saw it, just by sort of observation. But you can prove it mathematically, and I put that on our website if you want to look at it. The proof actually is not that bad. It's kind of nice how they do it. I wouldn't worry about knowing how to do it unless you're just curious. I was just curious, kind of, when I see things like that, yeah, that is interesting. Yeah, how did that happen? But okay, and the same, the proof I posted on there has both the mean and the calculation of standard deviation. It's pretty simple what they do. They do some nice little trick to make it come out simple. So if you're interested, it's on there under, I forget what I called it. I'll look and get out. Mean and variance, I think, for the binomial. So yeah, they're going to calculate it for you on those 2 that they had the example for in the previous slides. So yeah, we had 5 observations and the 10% chance of the event of interest. The mean was 1/2. Yeah, it looked like that, right? Yeah, standard deviation is kind of high. And the other one where we had 5 events and it was 50-50, remember the one that had the balanced. And so its mean is going to come up right in the middle, yep, 2.5, and its standard deviation is a little wider. Yeah. So you get a feel for this binomial distribution. Yeah. And the use of it. And here it is in Excel. And we already saw that. False, because if you don't say false, it gives you the sum, not the individual discrete probabilities, it'll give you the sum. Okay, so that's that distribution. So now we said we get 3. So now we do the Poisson. And so there is where you're interested in calculating the number of occurrences of something in what they call an area of opportunity. I would have probably used the word window of opportunity because I don't want you to think of area as strictly having to be area. It could be time, a window of opportunity. Time, area, volume, those kind of things. So yeah, very interesting, right? Yeah, they say it though. Yeah. Volume. Yeah. So the number of scratches on a car paint, the number of mosquito bites on a person, the number of computer crashes in a day. One of the common usages of it is the number of radioactive decays per unit time. I think the book said something about the number of fleas on your dog. So I don't have any fleas on my dog because I took your suggestion. I got the Seresto collars, and so my dog's happy. He has no fleas. I don't need a distribution to tell you that. So he's spoiled too. So that's all right. You got to spoil them. So again, if you want to count the number of events that occur in a given area, window, time, here's some things. Let's see. Yeah. You got to assume that the probability that things are going to occur in the same area are the same, right? Otherwise, it doesn't make any sense. So the amount of decays per time, the radioactive sample has to be the same now as it is in the next time. Or the dog's body can't have a bunch of flea treatment on it or something like that. And they're independent of each other, right? If I get a lot happening here, it can't mean that I'm having less happening over here or something. Yeah. Yeah, and the smaller the time, like time goes to zero, you're not going to have any opportunities. Or as you look at the smaller and smaller area on the dog's body, you're going to have no fleas. And so it only has one parameter. It's the average number of events per time, or per area, or per interval is lambda. So here is the Poisson distribution. You can see you can calculate these things by hand, and I will in some. So the probability that you're going to get X events in your window of time, given that you have this average events of lambda, is this. Okay, and again, if you're interested in the derivation, you can look for it. That's one of the things they do in an advanced statistics class might do that I do think is interesting, but would waste a lot of time. That would let you be able to use this. Yeah, and E. Yeah. E is a good old E number. So let's see. And again, here's the average of the Poisson distribution. Yeah, we said that, right? We said lambda was the average number of events per unit time or unit area. Here's the standard deviation. And again, if that doesn't look obvious to you, it doesn't look obvious to me. You know, and to come up with that and drive it, I'd have to think about it and have to do some math. And so, yeah, it shouldn't be obvious, but it is. You know, so that's okay, right? We can use it still. And there's Poisson tables as well. So here's an example. Let's see. Got an average number of 50, or a half. I mean, lambda's a half. So what's the probability that we got 2 events per unit, say 2 events per second, when we expect that we're only going to get a half of an event per second? So it's 8%. Yeah, you got a feel for that, right? If I thought I was only going to get 1 event every 2 seconds, what's the chance I get 2 events in 1 second? That's kind of what I'm asking. 8%. Yeah. Okay. So you can see how these are useful. I've got a process. I understand something about it. I know my lambda, say, and now I've made a measurement, or I've made an observation, I've made an experiment. I'm asking myself, well, was this likely? Just like the June birth month thing. Was that likely? Well, is this likely? Well, 8% of the time, I would say that's kind of an interesting experiment. Maybe something's up. Maybe I need to do more. You know, if I'd have gotten 80%, that's just things are going on like they should be. But maybe that's what I wanted too, right? Maybe it's a manufacturing process, but I don't want it to be wrong and weird. And then XL has the Poisson distribution, so you're going to have to have the lambda, right? And you're going to have to ask how many, and then again false because you don't want cumulative. So let's see. Yeah. So here's a good one we can see tabularly, and I put on the website too. I put in Chapter 6 and Chapter 5 Excel that's got an example of each of these in case you forget. So let's see. So here we're expecting 3 events per square foot, or 3 events per square inch, or the units are according to your problem, 3 events per second. And so now we're going to ask ourselves, what's the probability of getting 1, 2, 3, 4, 5, 6, to 15? So, yep. So here, low to get 0. Yep, we should get 3. It's interesting that 2 and 3 are the same. It just came out that way. And notice, unlike the binomial distribution, they stopped. Remember we had 5 samples, 4 samples, something like that. You can keep dragging the Poisson distribution out. Remember, it's got the E to the thing. It's tailing off. It's 0, but you need to at least, if you were going to look at the whole distribution, pull it out far enough to where it does go to 0. If you're trying to look at the whole thing, it doesn't quit. I could get 13 things, perhaps, maybe very unlikely, but unlike the binomial one where it quit, right? So here's a graph of it. Let's see, this is lambda equal half, x equal 2. So that was the question they had before. Right. So it's tailing off fairly rapidly. Yeah, because of that. Yeah, it tails off real fast. Yeah, that one tailed off faster than the previous one, right? Because it was lambda equal 3. Right. Here's lambda equal half, lambda equal 3. Yeah, here's the comparison of the 2. Yeah. So lambda equal to half, tailed off real quickly. If I'm expecting a half an event per area, it's very unlikely I'm going to get 7, And if I'm expecting 3 events per area, well, 7 is not quite as unlikely as it was on here. It makes sense, doesn't it? And the overall distribution makes sense. And the fact that it starts to kind of move this way makes sense, right? Here, if I'm expecting half, wouldn't be unusual to get 0. But here, I'm expecting 3. Yeah, it's unusual to get 1 and 0. So let's see. Now we're in the hypergeometric distribution. So we're now looking like the binomial distribution, where we had infinite population, infinite number of coin flips, or we had the machines that were broken, but each time we didn't throw any machines away. Each morning we asked ourselves, is there one broken or not? And then we kind of assumed we fixed them all overnight and asked ourselves again. So we didn't take the broken ones out and say, I had 4 today, I'm taking 1 out, now we got 3 tomorrow. That's either a finite population with replacement or an infinite population without replacement, it's infinitely repaired. The hypergeometric distribution would be the case where I'm taking from a finite population and I'm not replacing. So it would be the case where I said, well, I had 10 machines, one of them's broken, I'm throwing that one away, it's going to take me 6 months to get it fixed. Now I got 9. Okay, then next time I get broken, now I got 8. So that's when you would use it. So in trials from a sample, the finite population is big N. You're taking the sample without replacement, so therefore the outcomes of one trial is dependent on the outcome of the one before, right? If it was a negative, you threw one of them out. And you want to find the probability again of X items of interest in a sample where there are A items of interest in the population. Like we've been doing before, A is like the pi. So let's see. So N is your whole population, and A is the number of items of interest in the population, like the 2% of the broken computers in a pile of 1,000, say, so that'd be 20 of them in 1,000. N minus A is the number of not, yep, okay. N is your sample size, X is the number of items of interest in your sample, and N minus X is the number of not in your sample. So you can see what you're doing. Like in this case, say relating it back to the computer problem. I have 1,000 computers I'm buying from, and I knew from before that there was 2% of them were defective, so that says there's 20 defective ones in that pile of 1,000. I'm going to buy 10, and the question is, I'm going to say, is 2 of them, or what's the chances of 2 of them being defective? But as contrasted to the binomial question, remember we didn't just have 1,000 computers. In that case, we had infinite computers. We were buying them from Dell or whatever. In this case, we've got 1,000 of them in the computer store. So when we buy one, we've got 999 now. And then we buy an extra, we got 998. So it's going to slightly, if you calculated that and compared it to binomial, it's going to slightly, increase your chances each time you take one out. It's going to be a tiny bit more. It's that question like switching the door. Remember what show was that? Let's make a deal. Remember you switch the door, and that was one where Marilyn Vos-Savant got all in trouble for answering it. Do you guys remember that one? Did you ever read her? In the paper, the lady that does all the math questions or the science questions. You guys ever read her? I guess she's just not popular anymore. They had asked her the question. It's on the Let's Make a Deal. Remember that show where you had 3 doors and you sat around and you give me door number 1, and then they tell you they sit around and do a bunch of bull, and a lot of times they'd open up door number 2 and they'd show you some junk, why did they pick door number 2? And they'd ask you, do you want to switch? And so the question is, should you switch once you pick door number 1 and he showed you door number 2 has got a bunch of garbage in it, should you switch to door number 3 because are your chances better that you had the great vacation in the car? And her answer was, yeah, you should switch. And everybody was like, oh my God, no, the chances were 1 in 3. And you made your choice, you had 1 in 3, you picked one, you had 1 in 3 chances. And her response was, well, no, that's not true. Once you've been shown that door number 2 is not, then door number 3 has higher chances of being good. And people still say, no, I don't believe that. And so her explanation that did make sense to me was say, go away from 3 doors. Say there were 1,000 doors. And the grand prize is only behind 1. And so you went around, you picked door number 183, and then he showed you 998 other doors that were no. Would you switch then? You know, when you think about it, you laugh. Of course you would switch, you know. And so all the chances, the probabilities of those being right went into that other door, you know, and so, yeah, it's switched. So of course it had higher probability. But it's not intuitive, and so some of these things are kind of funny. But when you think about it, when you pull things out, your chances do go up a little bit there. And so here's the mean of the hypergeometric distribution. Same mean as the binomial, right? N times pi. Here's the standard deviation. Well, it was N times pi times 1 minus pi. So it's the same standard deviation as the other one, except you got this term on there, which is often called a correction factor. And remember too, we had that other correction factor earlier on in the class, where we had that discussion, should you divide by n or should you divide by n minus 1 when you're looking at the mean and the standard deviation of the population versus the sample. And so just again, I said I did a bunch of work this week. I have a book. Keep looking, always do it. Keep waiting for that. I have a book called Using Excel for Statistics. It's a nice book. I really like it, but I just randomly looked through it again the other day about this, and so online I put in his discussion on the n versus n minus 1 thing, because that's the best explanation I've ever seen as to why. So if you want to make sure that you completely understand why you would divide by n minus 1 when it's a sample, or divide by n when it's a population, read these 3 pages. Very clear. His explanation makes very good sense, and you will understand why you need to do that. And you will also then get some insight into why they do that correction factor on that hypergeometric. So it's probably worth reading. And this is that other thing I said I put up there, the proof of the variance and the mean for the binomial distribution. So if you want to read it, it's only a page or 2. These kind of things, sometimes they're worth reading, and even if you don't dig into them and do them, at least you see, I see it went long, page and a half. At least you see the math involved, and you see what somebody else does, and if nothing else, it gives you an idea of the technique, you know, or like with the n minus 1, that's a nuance, but it's nice to understand the nuance and understand why, and be able to tell somebody why. It makes you sound a lot smarter in the meeting. Even if you don't quite get it right, you just sort of know the reason. Well, it's a correction factor, if you will, to correct for the fact that you will over-predict, or you will incorrectly predict. Yeah, you will make your guess will be too small if you divide by n, then you divide by n minus 1, so you don't have that mistake. And so that's what this is doing. You see, it's a small correction. And as, let's see, as n gets big, if your n, which remember n was your total population size, if n is large and your number of samples is small, this kind of gets to be 1. You don't care. But if they're close to each other, it's going to make a bigger difference. Yeah, because, why? Because, yeah, if I'm pulling one thing out of 1 million and not replacing it, big deal, right? Even if I pull 10 things out of 1 million, big deal. But if I'm pulling 10 things out of 50, well, yeah, it shouldn't matter. So that's kind of what they're doing. So here, they're going to give you an example of how to use it. So we've got 3 computers are checked out from 10 in the department. 4 of them have illegally downloaded software. So what's the probability that 2 of the 3 that you selected have illegal software? So that's pretty good. All the numbers are different. Good. So we have our total population is 10 computers. And out of those 10, 4 of them have the thing of interest. The thing of interest is illegal software. We're going to pull 3 of them out, and we're going to pull, and we're not replacing, right? We're going to get one, we're going to get another one, we're not replacing them. And our question is, what's the chances that 2 of them, out of the 2 of the 3, have the illegal software? So just plug them right in, right? Let's see. 3. So 30% chance. That's kind of interesting. Yeah. Did they did not define what their little symbols. Oh yeah, they did. Yeah, they did, didn't they? Yeah, it's that C, the counting thing there. Okay, so they defined. I was just saying they didn't define what those are, but they did. Remember the counting formula way back early, several view graphs earlier. That's just a way of writing the terms in the counting formula. Oh, I thought they got to show you that, or this is not any good. Of course, you don't have to. You can do this, right? Yeah. They should, you know, one of the things they should do, this is funny, look, if it were me and I were making these view graphs, I would do this one, this example in Excel, right? The next one, they show you Excel, they got a new one. Now in this case, they've got, their total population is 30. There's 10 events of interest in the 30, and we're going to pull 8. And then now what's the probability? We got 0, 1, 2, 3, 4, 5, 6, 7, 8. So let's see. In general, we think we're going to get 3 of them. Yeah. And you know, in your head, you probably would have told me that, right? I got a population where 1 in 3 of them have my thing of interest, right? Whether it's illegally downloaded software or there are 10 black marbles out of 30 total or whatever. And I pull a sample of 8. You know, just off the top of your head, you'd say, well, yeah, 1/3 of them probably going to be bad, right? So 2 or 3, and so 2 or 3, yeah, you've got a feel for this kind of stuff, even though you may think you don't. But you know, you would have done that. Yeah, I would have said that. And 3 is probably more likely than 2, yeah, because I guess not much more though. Yeah. So what's the chances of all 8 of them having it? Yeah, almost 0, right? Yeah, of course. Yeah, what's the chances of none of them having it? Pretty darn low, too. I see that. So you can see the use of this, use of these things. That one particularly in some of your problems. So what did we do? We talked about discrete variables, things you can count as opposed to things you measure. We talked about the covariance as we were relating positives to positives, negatives to negatives. And then we had these 3 distributions, the binomial, the Poisson, and the hypergeometric. And remember, this was, we had a probability of an event of interest, and we had so many, a finite population there. This one, we had an average amount in a window of interest, and it kind of went on forever. And this one was the same as that one, only you didn't replace. You weren't pulling from an infinite population, or you consumed them as you replaced them. As you pull them out, I mean, you didn't put them back in. Let's see. So now I've got some examples to work. So let's see. Let's do Let's do 5-2 first. Let's see here. 2. Well, 5-2 may be different in your book, but that's all right. I'll put the whole problem here anyway. So I think 5-2 is just a generic problem where they're saying we just come up with the expected value and the standard deviation for a given distribution. So it's just a given set of data you've made from a discrete system. So let's see how it reads. So mine says, here's a table containing the probability distribution for the number of traffic accidents. Oh yeah, I wrote it up here. Okay. So the number of traffic accidents in a small city. Okay, so we have 0, 1, 2, 3, 4, 5. And here's the probability that happens. And again, it should add up to 1. So that says they've never had a day where they had 6, 7, 8, 9, or 10, or if they did, they've just thrown that out, called it an outlier, and said we're not going to deal with that in our analysis. And so now the first question is, what is the expected value? Okay, so remember from our very early on formula, the expected value was each possibility times its probability and summed up. So I've got each possibility, 0 through 5. Each of the probabilities, there's the product, that times that one times that one, that one times that one. Adding them all up, and so your expected value is 2. Okay, does that make sense? This was what this is. Should check. I just added those up and check. Does that make sense? Yeah, look at the probabilities. I would say that given that distribution of traffic accidents in that small city, I would expect to have 2 every day. Right? And again, I think you would have intuitively known that, right? Looking at it, you would have said, look at this table, 45% of the chance, 45% of the time of our data we have 2, and kind of around it, 20% we have 1, and almost 15% we have 3. Yeah, I'd say I'd expect 2 every day. Now, but we mathematically can figure that out. Okay, now, but now the other question is, how much variation do we have? Do we think we're very likely to get 0 or 1? Well, let's look. So there was the formula too, by the way. I stuck it in there. So you got it. And all these are posted too. So what's the variance or standard deviation? Remember, it was each value 0, 1, 2, 3, 4, 5 minus the expected value squared. So your distance away from the expected value. And again, I think if I'd never defined variance or standard deviation for you, and I just said, give me some sort of idea of how this thing spreads out, I think you would have made that up. I think so. I think you had enough thought about it. You would have said, yeah. How far is each one of them away? Or maybe you wouldn't have squared. Maybe you would have taken the absolute value. That would have been okay too. But you would at least try to say, well, I can't let ones on the left and the right cancel each other and make it look good, and then multiply by probability of it happening. So the spread is around 1. Well, we saw that in the data, didn't we? It looked like the average was 2, and there's a pretty good chance you might get 1 or you might get 3. Very unlikely that we were going to get 5 or 4, and very unlikely we were going to get 0. So, yeah, so even the math works with your intuition, and I think it should. Well, that's all there is, that's all. Yeah, that's too easy. Okay. So now we go on to next 524. I think that's right. So it's the number of failed LEDs. Maybe it's different too. I'll read you mine. It says you're manufacturing and you're doing quality control, and you know that the failure rate for your LED lights is 5%. Yeah, okay, let's make a small one. We'll put it up for you. So your failure rate's 5% on your process. There we go. And suppose that you pull 10 of your LED bulbs out of your manufacturing process, and then what's the probability that, and we got 4 cases, that none of them were defective, that exactly 1, that you got 2 or fewer were defective, or 3 or more were defective. Okay, so we've got a process, and our thing of interest is failure, failed LEDs. So our probability of failure is 5%. So our thing of interest is it defective, is it failed? 5%. We're going to pull a sample of 10, and we're kind of curious, what's the chances that we got some number or so of these 10? So this is binomial, right? Yeah, it's binomial. We pulled a sample out of an infinite population. They didn't tell us we had 100 LEDs sitting on the shelf. We had the whole manufacturing process. It's infinite. We keep on going. And so here, so it's not the hopper geometric. So our sample size is 10. Our pi, our interest, is 5%, 0.05. And so the first question is, what's the probability that we got 0 of them out of this sample of 10 with the population percentage of interest being 5%? So I just applied the formula just like it's supposed to be, although you probably can't. You know, that says 10 factorial divided by 0 factorial by 10 factorial, 0.05 to the 0, 1 minus 0.05 to the 10. That's a good one to ask, isn't it? Because basically, you could have done that without knowing the binomial distribution, right? I'm telling you, you've got a 5% chance of getting a bad one. And what's the chances that you got no bad ones? All right, so it's the 95% chance of getting a good one 10 times in a row, right? I pulled 10 samples out, had 95% chance of getting a good one 10 times. So I had to have 0.95, 0.95, 0.95, 0.95, 10 times, right? So and that's what this formula came out to be. Okay. Now, granted, using the binomial it came out that way too. The 10 factorial canceled out. 0.05 to the 0th power is 1. So here you have the 1 minus the 0.05, which is the 0.95 to the 10th power. So it's nice to know that you could apply this distribution, and also you could apply what you would think logically should have happened. I had to have, I had that 95% chance of getting a good one. I had to do that 10 times in a row. It also kind of gives you a little hint too that, yeah, even if you're 95% successful, if you do something 10 times in a row, you're going to fail. You only have 6% chance of getting them all 10 be good. It's the same question as having 0 defects. Yeah. Even people who are almost perfect don't apply as you go on forever. A lot of them did. So what's the chance of getting 1 out of it? So now it's 10 factorial, 1 factorial, 9 factorial. Remember the formula. I have it up there. Yeah. 0.05 to the first, 1 minus 0.05 to the 9th, 31% chance of having 1. Okay. That was not hard. That's a straightforward application. Now the next one is a slight tweak, so it's worth showing. So now the question is, what's the chance of getting less than or equal to 2? So we're not asking what one value, not 1, 0, or 2. We're saying less than or equal to. Well, that's easy. That's the chances of getting 0, plus the chances of getting 1, plus the chances of getting 2, right? Yeah, that makes sense. Well, we've already answered the 0 one, and we've already answered the 1 one. Part A and B calculated those first two, so I do need to calculate this one. Chances of getting 2 with 10 samples at 5%, 10 factorial, 2 factorial, 8, 0.5 to the second, 1 minus 0.5 to the 8th. So you kind of start seeing the pattern, and it does make sense, right? Twice I had to fail, 8 times I had to succeed. Yeah, that's right, to get 2 bad ones, or 2 defective ones. Okay, so there's that number, so add all 3 of them up. 99% chance that I got 2 or less bad ones. Yeah, that makes sense to me. And then what's the chances of getting 3 or more failed ones in my sample of 10? The easiest way to calculate that, we could add up what's the chances of getting 4, 5, 6, 7, 8, 9, and 10. We could have done that. Or we could just take 1 minus the chances of getting 2 or less. A little bit easier. But it would have come out the same. I didn't want to do it, but it would come out the same if we calculated 3, 5, 6, 7, 8, 9, 10. You can tell it's starting to get small. That's a good question, I think. When it makes sense and could be applicable to anything you're doing. All right, now let's see. I think I put 34 in here too. It's pretty good. It's 30 or 32. I'm sorry. 32. I also did on excess. Let's see. So problem 32 in my book is you're making chocolate chips, and you're throwing chocolate chips in the cookie, and you know that in general there are 6 chocolate chips in each cookie. So this is starting to point to Poisson, right? I've got a number of things happening in an area of interest. My area of interest is a cookie, which is a good example. That's why I liked it, because it's not square inches, it's not seconds, it's a cookie. Okay, that's cool. And we got 6 chocolate chips in it, which I would have liked. My wife thinks chocolate chips. Usually puts like 20 in each one. That's much more important. So now the question is, what is that? Well, it's a Poisson, right? Let's just tell you, Poisson type distribution. There it is, very was simple. And so, what's the average? Well, I told you, there was an average of 6 per cookie. So now the first question, I should read, what's the chances that we got less than 5 in each one? So yeah, I don't know why I put a 6 in there. I put a 6 in there. I think the open was free. Yeah, I shouldn't have had a 6. That should be a 4. So the probability that x is less than 5, I want to look at the probability of 0, 1, 2, 3, and 4. So if that's a 6 like it reads, it's a mistake. So you can see I've done 0, 1, 2, 3, and 4. Now what I did do in my math, I factored the e to the minus lambda out of all of them, since e to the minus lambda is common to all of them. The only thing that changes in the formula is x, which is x is either 0, 1, 2, 3, or 4. So I put it out front. So the chances that you have less than 5 chocolate chips is 28%, 29%. Yeah, less than 5, yeah. What's the chances that you had exactly 5? Well, e to the minus 6 times 6 to the 5th power over 5 factorial, 16%. And what's the chances that you had greater than or equal to 5? Well, it's going to be 1 minus the chance that you had less than 5, 71%. Okay. And let's see, what was D? What's the chances that you either had 4 or 5 in it? Yeah, let's see. So here's 4. E to the minus 6, 6 to the 4th over 4 factorial. Here's 5. E to the minus 6. That e to the minus 6 is always the same. 6 to the 5th over 5 factorial. So 29% chance that you had 4 or 5. Both of those chances. Yeah. An interesting question. You can see how this would be useful. Let me see. Let me show you how it looks in Excel. Because it's probably easier to work even in Excel.
Dr. Preston, now, obviously, this is hypothetical. So this is assuming that all the cookies are the same size.
It is.
So then how would you factor in?
Or it assumes that she puts the same amount in each cookie regardless of what size.
Okay.
Yeah. So what if you want to have different size cookies, then I would not have the area of interest be a cookie. I would have it be square inches or square feet, whatever you want. But yeah, the area of the cookie. So then you could do that. And then you would have to calculate, it wouldn't be 6 anymore. It would be 6 divided by, the area of a cookie, or you'd have to do some more experiments rather than just count them. You'd have to count them and measure the area. You could do that. Which is good, you're right, because they're different size cookies. Or that you might have different quality cookies too. You might have the crappy ones and the good ones, and then you'd have to do it twice. You wouldn't have 6, you'd have 12 or something. The good ones. Let's see. Oh, come back. Okay, so here's what I did. I did it in Excel. I did one of my color things again too, just to show you. Because the colors are always worse here. So here's the Poisson distribution with lambda equals 6 for 0, 1, 2, 3, and I just kept on going. Remember, I said it keeps going until you get down to 0. So I pulled it down a long way. In fact, I guess I had to pull it. I know why, because I did it 2 ways. So the first question was less than 5. So less than 5 was the adding 0, 1, 2, 3, 4 only, right? So that's this yellowish color. And so I just added those up. In fact, I didn't even do anything more than, really, I worked this problem in 3 seconds, literally. I put the Poisson distribution in here. You can see, you can't see, lambda. There's lambda. This number is that one, as I counted down, and false because I want each discrete. I don't want to keep cumulative. And then when I want to know this, I just put my little square around it and let it sum it up for me. I don't even have a formula over here. I just let it sum and type it in. So the probability of it equaling 5, that's just this one number, right? And then the probability of greater than or equal to 5, rather than doing the 1 minus thing, I thought that might be interesting. Let me just add them all up, right? So I added them all up until I got where I was satisfied. It was pretty much 0. Not quite 0, but that's 0 enough for me. So, you kept going, but that, to be silly. And then the other question, the probability of 4 or 5 is just the sum of those two. Yeah, here I even made that column. So you can see, even if you don't want to use your calculator and plug in those formulas, here it's not hard. Poisson disk is not hard to do. It's only one value. In fact, I didn't even have to put lambda out here. I could have just put a 6 in there. It would have been even quicker. And so it's not hard to use, and as long as you recognize that this is needed a Poisson distribution because it's a number of events in a given amount of time, or a number of events in a given area, or a number of events in a given thing. And you don't know, just, I guess for me, like when I take these kind of things in class, I maybe try to remember one example. Like for me, the one that keeps sticking in my head is the number of nuclear decays for a certain amount of time, because I work at Y12, and that is something you might care about. So if you can just remember that that is a Poisson, then hopefully if you find another thing and you think, oh, that's like that nuclear problem or something, oh, that must be a Poisson. But maybe you can't remember that. Maybe you can just remember, well, darn, in that statistics class, we did talk somewhere in there about things that fit in a certain area of opportunity, and I can go look it up, and hopefully you remember that that's discrete, and you can find chapter 5 quickly. Because I can't remember all these things, but you can mostly remember something. So let's see. I think that's it, except for, which is the timing. That was it, right? I showed you the. Oh, I know the one thing I was going to show you. I know one thing that was hard. So I made that comment. So, if you do need more sophisticated statistics capabilities, R is there, R is free, download it, use it. It seems easy to use. I'll play with it this whole semester. I'll throw a couple other things in for you. For example, let's see, let me just show you. Remember, I struggled, and Excel killed me. It took me almost an hour to make that silly box plot that was bad. And so, here's their example, but I wanted to make a more simple example. Let's see if let's see, now that should be, this is all their stuff, isn't it? Mine is under notes, I think. I have my own notes here. Let me grab those for you, because I want to show you how easy it is to do a box plot. You will be amazed. So the R notes, which is on your website, shows you that's the main page for R. It's got all the junk, the manuals.